Okay, so for the introduction, the purpose of this lab was to track the motion of a spring and ball system to determine whether or not it followed the energy principle, using by comparing a experimental and a computational model of the ball and the spring. So the fundamental principles at work here are going to be Newton's second law, and the energy principle, and the momentum theory equations that we derive from Newton's second law, and the energy principle equations. So for Newton's second law equations, we're going to say that, F equals ma, velocity equals initial velocity plus acceleration times time, position, and this is on a symplectic integration calculation. Position equals initial position times velocity times time, where time is change in time, if we want to be more specific. And then for our momentum theory, we're going to say that if there's no work done by the system on the surroundings or on the system by the surroundings, we can say that the change in energy equals 0. And from that, we can say that all of our changes in energy have to equal to 0. For this one, we have three sources. We have two sources of energy. We've got the spring, we've got gravity, and I guess kinetic energy is part of that mix too. So kinetic energy and gravitational potential energy change, and at the same time, so does the spring potential and kinetic energy. So it's from energy, it's from gravity and the spring, and they each have kinetic and potential energy stored up. And then, so for gravitational potential energy, obviously we can say that UG at any given moment is mass times gravity times the height, and change in UG is just, the current gravitational potential energy minus the initial gravitational potential energy. Our spring is obviously negative. Our spring force is obviously negative K times S squared, where S is the stretch in the system, and our energy is 1/2 K times the stretch squared. And finally, our kinetic energy is 1/2 mass times the velocity squared, and that one's pretty simple to do because that's just multiplication there. And so with those, we can piece together the entire movement of the system, and we can derive the energy at any given moment in the system and make sure that it equals 0. Because again, we're saying that this is an isolated system, therefore it has no energy transfer, so the total change in energy should be 0. So here's our experimental motion. As you can see, we've got an oscillation in both the x and y direction, and here at the bottom, you can see kind of. Hold on, sorry. Where's my? I can't find the pointer. And you can see the positions at the bottom. You may look if you want to. They're not that interesting. So our initial conditions, our system's going to be the ball and the spring. Our surroundings are going to be nothing. That way we can make the math a little bit easier on ourselves and say that there was no work done on the system. The initial mass of the ball is 0.402 kilograms, and the spring constant, K, is 6.83 Newton meters. Or newtons per meter, sorry. Getting into our computational model, here are our initial conditions for the computational model. As you can see, you got mass, position inputted. The thing starts with 0 velocity, so we have that noted. We've got G is 9.8 because that's universal. That's a constant on Earth. K is 6.83, and L naught we calculated algebraically. And then L is going to be equal to the position of the ball at the moment minus the origin of the spring, because that's just how we define the stretch length of the spring. Let's see. Okay, here at the bottom we have our energy equations. So K, we talked about them earlier, but K equals 1/2 mv squared. Gravitational potential energy equals mgh. Spring potential energy equals that should be a 0.5 K times 1 times x squared. And then total energy is all those summed together. Here's our calculation loop. We calculate our initial energies. We calculate the force due to gravity in the spring. We add those together to get the net force. Take the net force, you divide it by the mass, get the acceleration to get the velocity, with which we get the position. We update the position of the ball to update the position of L and L hat and S in order to figure out what the new stretch length of the spring is. And then we put that back into our energy equations. We recalculate those. We've already talked about those twice, so I don't think we need to go back over them again. Here are the results. So as you can see, the energy is correct. That's how it should look. There's a stretch error on the positions. I don't know why that is. That's my fault. Somewhere in the code, I have an extra order of magnitude that I did not mean, but I couldn't find it. So, is the energy principle satisfied? To put it simply, yes. The total change in the system energy is 0, and because we're saying it's an isolated system, it should be. So that looks perfect. Why are and then for the other question, why are the oscillations different? Because of the materials properties of springs in the x and y direction differ based on the Young's modulus, but that's not really relevant to this class. Finally, source